So this video is gonna be uh, about more kernel examples. So in this video, I'll try to cover two things. One is grid refinement. So one of the advantages of SW4 is that it allows um, denser grid closer to the surface. So usually the velocity model the seismic velocity increases with depth, so the wavelength increases with depth. So um, if you are using a uniform mesh finite difference code, then the grid spacing is fixed throughout all the depths, right? So what you have to do is to actually pick a grid spacing that's like a uh, 1/5 or 1/10 of the shortest wavelength, right? And I was saying that the wavelength increases with depth, so the shortest wavelength is usually determined by the slowest velocity, which is close to the surface. So if you are using a uniform mesh finite difference code, then the grid spacing has to be very small. It's kind of pretty much fixed by the smallest velocity that's close to the surface. But SW4 allows you to vary grid spacing uh, with depth. It doesn't allow you to vary grid spacing laterally, but it allows you to vary grid spacing or to increase grid spacing with depth. So that's one of the advantages of SW4. And um, so let's look at that. We're still gonna use this half space example that we did last time in the last video. Um, but we added one more example. That's the surface waves. Right. So these are the kernels. This is the source receiver cross-section view for a Rayleigh wave um, between the two points. Right. You can think of it as ambient noise tomography. So the receivers are acting like a virtual source. So you have one virtual source on at one of the stations, and then the other station acts as a receiver. So and these kernels are for the frequency dependent group delay time. This one is at 0.5 hertz, and then this one is at 2 hertz. And you can sort of see that at lower frequency the wavelength is longer, so the sensitivity is the kind of deeper, has larger sensitivity at larger depths. And then at higher frequency the sensitivity is shallower, right? So this is cross-section view to show the depth extent of the sensitivity, and then this is sort of the map view. We're looking from the top, and the largest sensitivity actually varies with depth with frequency. So for the 0.5 hertz kernel, the largest sensitivity is actually at about 1.6 kilometer depth. And then for this 2 hertz example, the largest sensitivity is actually at 400 meter depth. So this one was plotted at 400 meter depth. This is a map view plot at 400 meter depth. And then this is a map view plot at about 1.6 kilometer depth. Right. So it shows the largest, the sensitivity at the largest, the largest sensitivity for this frequency dependent group delay kernels. So this is group delay, but if we are using phase delay, the kernel could look quite different. In particular, the sidebands, all those sidebands are going to be attenuated more, right? So you won't see very strong sidebands. But for group delay kernels, you're going to see some kind of very strong sidebands. But it's kind of okay because when you are actually doing a realistic inversion, you are inverting many frequencies simultaneously. So all those different sidebands are going to cancel out or average out. What's actually having real effect is actually the sensitivity in the middle. So that's kind of typical for inversions with this kind of frequency dependent kernels. And But so let's, and then I also made some changes to the code for creating the WPK or wave field perturbation kernel. The last time I was talking about the WPK code, a sequential code that's generating wave field perturbation kernels, and I've made some changes to that. I will try to actually explain those changes also. So. Uh, Again, this is Cheyenne. I'm on that big computer at the Anchor Wyoming Supercomputing Center. Um, so, so, so the first thing we're gonna do is to look at the forward simulation code, right? The input to forward simulation code to SW4 actually. So if we look at the 1001, look at this particular example, you're gonna see some of the differences in terms of the input file. Everything else is kind of similar to the last video, and then the only thing that's kind of added is this line called refinement Zmax equals to 5000. So this refinement keyword basically tells SW4 to refine or to to uh, to to double the number of grid points above this particular depth. So this grid command, you can think of the grid command as some kind of defining the coarsest grid, right? So the coarsest grid is going to have a grid spacing of 200 meter, and then we're going to have 351 grid points in the x direction, 151 points in the y direction, and 251 points in the z directions, right? So that's like the coarsest grid, and this coarsest grid is going to cover if you multiply 250 to like a 200 meter, that's like a 50 kilometer, right? That's like a 50 kilometer. So the entire simulation volume is gonna extend to like 50 kilometer depth. And then this refinement keyword basically tells SW4 to refine or double the number of grid points above this particular depth. That's 5,000 meters. That's 5 kilometers. So we want to refine the mesh above 5 km 5 km depth, right? So that means that above 5 kilometers, from 0 depth to 5 kilometer depth, the grid spacing is going to be 100 meters. So every time you write a refinement keyword, it's going to reduce the grid spacing by half. So if you have multiple refinements, suppose I add one more refinement command with z max equals to like a 10,000 something, then the 10,000, so then above 10,000 grid spacing is going to be 100, right? And then if you still keep this refinement keyword, that's 5 km. So above 5 km, it's going to be 50 meter. So every time SW4 sees a refinement keyword, it's going to reduce the grid spacing by half, right? And then it's going to do that kind of reduction according to depth. So it's going to start with 200 meter grid spacing at the largest depth. That's like a 50 km, right? And then it's going to go up, right? Every time it sees a Zmax refinement, Zmax, it's going to reduce the grid spacing by half. So that's how the refinement keyword can be used, right? And then since we have changed the mesh, right? So in the last video, we were using a uniform mesh. It's not really, there's no grid refinement at all. It's a uniform mesh with 200 meter grid spacing throughout the entire 50 km simulation depth, right? But this time the mesh has changed, right? So every time the mesh changes or the velocity model changes, it's kind of important for us to go through this process. So if the mesh changes, we have to do another write invo equals to 1 to write out the grid, information, and then increase the write invo to 2 to write out the updated velocity model, and then increase the write info to 3 to actually run the simulations and write out the strain views, right? So every time if we change the mesh, we have to sort of go through the process again, We have to sort of increase it from like 1 to 2 to 3 eventually. And then another thing that I have changed is this ANT skip. Because I have refined grid, so storage is going to increase. We have to sort of store the wave field on more grid points. So one of the ways to reduce storage is to actually reduce the time sampling rate, right? So in the last video, I was using NT-SKP equals to 1, so there's no temporal decimation. Here I have a temporal decimation factor of 2, right? So I'm saving the strand fields, or I'm saving the strand fields every 2 time steps, right? So, and then what else? I changed nx skip, ny skip, and nz skip, these 3 parameters to now these parameters has 2 numbers in it, right? These are for the composite grids or for the individual component grids. So I have a decimation grid for the bottom grid without any kind of refinement. That's my decimation rate for the bottom grid without any refinement. That's the 200 meter grid spacing. So after a decimation rate of 2, then I'm saving like 400 meter per. The grid spacing after decimation is like 400 meter. And then for the refined grid, that's on the top, I have a decimation rate of 4. Right. In the refinement grid, the grid spacing is 100 meters. So decimation rate of 4, it's gonna give you 400 meter grid spacing for the recording grid. Right. So the recording grid still has a 400 meter uniform grid spacing. Right. It doesn't have to be. The code is not really restricted, or the inversion code is not restricted to this kind of uniform grid spacing for the recording grid. But for plotting purposes, for the purpose of generating plots, it's kind of easier to write some MATLAB scripts to plot those kernels. So here, that's why I did this thing. Right. So every time you refine the grid, this is just the 2 component grids, right? But if you have like a multiple refinement statements in your simulation, then you have more than 2 component grids, and then in that case you have to sort of specify more numbers for each of the decimation rate in each of the component grids. Yeah, and then everything else is like identical to the previous video. So we're gonna well, if we want to look at the files created in the model directory, then you still got all those similar files, but the content of those files are going to be different. Suppose we want to look at this wf000.info. That's the grid info file, right? That's the grid info file. So now in the last video, it was just a 1 line with the 0 squared, right? But now the 0 squared is still there, right? But now you have another line. It's 2 lines. So the number of lines actually depends upon the number of component grids. So the bottom grid is called grid 0. It's going to have an index of 0. And then the grid on top of it is going to have a grid number 1, right? So the grid number actually increases from larger depths. To smaller depths. But this is kind of against the SW4 coordinate system. The SW4 coordinate system actually has a z number that's pointing down, z-axis pointing into the Earth, right? So z is supposed to increase with depth, right? But the grid number that's used inside of SW4, the grid ID, actually goes the opposite way. So the grid ID actually increases towards the free surface. So the bottom grid, the coarsest grid, is going to have a ID of 0, right? And you can sort of see the number of z grid, right? So the top 5,000 meters are going to have a grid spacing of 100 meters because we did 1 refinement, right? So 5 kilometers, that's like 51 grid points. That's exactly 5 kilometers, right? Yeah. And then that's the sort of the grid information, right? That's the grid information. And then if you look at if you look at this particular file called grid.info, then you're gonna have 4 lines here. Last time I was saying that you're supposed to have this is actually the maximum, the bottom depth of the 0th grid, and then this is the bottom depth of the first grid, right? So the bottom depth of the 0th grid is supposed to be like a 50 kilometer, right? And then the bottom depth of the refined grid 1 is supposed to be like a 5 kilometer depth, right? And 5,000 meter. And then the grid spacing for the bottom grid without a refinement, that's 200 meter. And then in the refined grid, that's like 100 meter. So that's this file. And then if you want to look at the recording grid file, it's gonna look like that. So for grid 0, we're gonna have on this particular process, that's 0000000. So the process, the MPI process are kind of numbered in a 2-dimensional way. So so for this particular process, for the mesh that lives on this particular MPI process, you're going to have 2 grids, right? 2 recording grids. This is the recording grid for, this is the number of recording grid points for grid 0, and then this is the number of recording grid points for grid 1, right? And then all the grid IDs are kind of following that, right? So for all the lines that's following these 2 numbers, the first 11300 lines are going to be the recording grid IDs, grid coordinates for the 0th grid, and then the bottom 1300 lines are going to be for the recording coordinates for the bottom grid, right? And then you also have the Z files, that's the topography, but for now we don't have topography yet, so these files are just the recording zeros, very small files, doesn't really matter. And then these are the velocity model, the VPVS and density. We're doing an elastic sort of example, so VPVS and density on each of the recording grid, that's pretty much the model file that's created by using and then let's FWF. Yeah, then that's pretty much it. And then we can just run our simulations to create all the strand views and stuff, right? And then the synthetic seismograms are not going to change too much. It's how do I say? The synthetic seismograms are like there are some very small changes, right? So for this body wave example that we are actually looking at last time, for this particular, so source is here, receiver is here, right? And then we're looking at the 3 phases, right? Direct arriving P, surface reflected P, surface converted P to S, right? For this particular example, the seismograms are synthetic seismograms are not going to change too much, especially for the P and S. For this direct arriving P, right? You might see some small changes for those converted and reflected phases because they interact with the free surface, and now we have densified the grid that's closing to the free surface, right? So you can expect that the seismograms, the synthetic seismograms for those phases could become slightly more accurate. Do I still have that example? Maybe I should try to make a plot of it, but let me see if I still have the seismogram. Okay, I still have the synthetic seismograms. Right, this one was like without the grid refinement. This one was with the grid refinement. Let me just plot them and say, so we can sort of take a look at the. So this is gonna be without the grid refinement, right? Oh, only final function. I forgot to add the path. We have to actually add the path of SW4's MATLAB code, and then we can call read USGS, and then that's with the grid refinement. Then let's call it 1, 1, 1, 1, right? And then let's just open a new figure. I'll just plot the x component. Maybe I should just use a black hold on. That's like without the refinement, right? Without the refinement, so you can sort of see some small wiggles, some kind of maybe numerical noise, right? And then let's plot the T1 VX1 with red, right? So now you can sort of see the differences. It's really minor actually. The only thing that's kind of substantial is probably here for this particular phase, because this particular phase has smaller amplitude, right? And then the difference could be slightly, sort of relatively bigger. Can I blow up this view? Yeah. You can sort of see some so numerical dispersion, and then all those wiggles, all those things are kind of numerical. It's not real. And then one of the things that's kind of important is temporal sampling interval of the synthetic seismograms. So once you have refined the grid, spatial grid, the time sampling interval is going to reduce by half. So if you look at the T2, the second element subtract the first element for the time without the for the synthetic without the refinement, that's like 0.0318, right? And then if you look at the same number, the time step for the with the grid refinement, that's exactly 1/2 of it. See, that's because we reduced the spatial sampling interval by half. I mean the minimum grid spacing. We reduced the minimum grid spacing from 200 meter to 100 meter. And then the time sampling interval is kind of determined from the spatial grid spacing by using the CFL condition. So in order for the simulation to be, in order for the time stepping to be stable, we have to use a certain formula, right? So the time step length has to be kind of proportional to the spatial grid spacing, to the minimum spatial grid spacing. So you can just see the time sampling. So if you look at the peak, close to the peak, without the mesh refinement, the time sampling interval is like you can sort of see those kinks. Those kinks, that's the time sampling points, right? And then for this one, for the red curve with the improved with the refinement, you can sort of see the time step length is like 1/2 of it, right? And that's one of the reasons for actually reducing the time sampling temporal decimation rate, for increasing the temporal decimation rate, right? So if I increase the temporal decimation rate from 1 to 2, then the temporal sampling interval for the strand fields are going to be identical to the previous video, right? So I won't increase the storage because of reduce the time stepping time steps. Okay, so that's the synthetic seismogram, right? And then what else do I have to sort of explain? Let me see. So once we got the synthetic seismograms, all we have to do is to actually, because the windows has been picked already, right? So for the three phases, the temporal window is still the same, right? So it's still the same temporal window, right? But you can sort of see the file has changed the format somehow, right? Last time it doesn't have the first two numbers for each of the row, but this time it's you've got these two extra columns, right? And these two extra columns actually has a meaning for it. And this is the second thing I want to talk about. It's it's the change I've made to the code for generating the WPK files, or the WPK code, wavefield preparation code, wavefield preparation kernel generation code. So um, so 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 because the window isn't, because the synthetic signal isn't changing too much, so the temporal window is not going to change, right? So that's the three windows. So this window is for the direct arriving P, this is for the surface reflected P, and then this is for the surface converted to PS converted wave, right? Um, and then um, these two columns are what? These two columns are um, so last time the WPK core, the core to the WPK binary actually involves lots of inputs, right? Command line inputs, I mean, right? But now the command line inputs has been reduced to like just two. The command line inputs, one is the inversion control file, the inversion parameter file. That's inv.in. That's the file that that's this file. That's this particular file, right? And then the second file is called win.lst. Win.lst is just a list of the windows of the window files. I mean, these kind of files. So if I look at the content of it, so win.list is where is the link? Win.list is writing my job directory. So if I look at the win.list, it's got two lines because it's got two windows, two window files. This window file was for that body wave example, the half space body wave example that we're looking at. We've been looking at, right? So you have the window file, and then followed by the window file is the the source time function used for computing the receiver green tensors. That's the g1.dat file, right? Last time I was specifying this particular file as one of the command line inputs, and later on I realized that this file could be different for different windows actually, right? So if I actually use this as a command line input, then WPK is gonna process every window using the same receiver green tensors, right? But in reality, you may want to use different source time functions for different different receivers, right? And then this number one indicates, because this g1.dat file has like multiple columns. It actually has 4 columns, right? So this number one just indicating which column is supposed to be the source time function. Right? So the 0th column is supposed to be time, and then the first column is supposed to be the source time function, right? And then the last number is actually the beginning time step. I want to write out my WPK time series, right? Last time I was saying that in order to actually get the hole in the donut hole in the middle of the body wave kernel, I have to skip like 2 points, right? 2 their time steps. But since I have refined the spatial grid, so the time step length, time sampling interval has reduced like by half. So 2 time samples is now 4 time samples actually, right? And then in the last video, I also have another command line input parameter which is the temporal decimation rate, right? But this temporal decimation rate actually is inside of the inversion input file, inversion control file. That's the NTSKP, right? And you don't want to use a number that's kind of different from the inversion control file. So that's why this decimation rate, temporal decimation rate file input is kind of removed, because it's now read from this control file. Yeah, I think and then the WPA code is going to read this input file actually. It's going to read this window file. It's going to read the window file. It's going to take the last 4 numbers as actually the temporal window for isolating the particular arrival, and then it's going to look at the first 2 numbers, the first two numbers. Um, these two numbers are kind of a okay. So these two numbers are actually, one is the channel number, and then the second number is actually the kernel, the WPK type. Right. What I was saying is that uh, depending upon the kind of misfit measurement you are actually using, so the WPK has to be computed accordingly, right? So for broadband cross correlation WPK, or for broadband cross correlation delay time WPK, the flag is 0, right? And then for frequency dependent group delay time, the flag is going to be 1. And then if I add more WPK implementations, then they are going to have more additional numbers, right? Um, and then the first number is going to be the channel number, because most of the synthetic cytograms are 3 components, right? So you got X, Y, and a Z component. So 0 means the X component, because the three arrivals that we're actually using for computing the kernels are all on the X component. So for the 3 windows, the first number is always 0, and then we are computing the broadband cross correlation delay time for the 3 windows. So the second number is also all zeros, right? But if you look at the surface wave example, it's going to be different, right? So if I take a look at this particular window, you can sort of see we actually have only one window indicated by these 4 numbers, right? One window, one phase, that's the Rayleigh wave. And this Rayleigh wave is actually on the Z component. So X component is 0, then Y component is 1, right? And then Z component is going to be 2. And then we are doing frequency dependent, we are making frequency dependent group delay measurements. So the second number is going to be 1, the WK flag is going to be 1, and then this is the window, right? These 4 numbers are going to be windows. And then don't forget, for frequency dependent group delays, the WPK are actually frequency dependent. So depending upon the frequency at which you are making the group delay measurements, the WPKs are going to be different. So you have to tell the WPK code which frequencies you are actually making the measurement on. So we are making measurements on 0.5 hertz and 2 hertz. So this unit is hertz, right? So that's the kind of convention for the window file now, right? What's actually the benefit of doing this thing, right? Because sometimes on one cytogram, you might want to pick multiple windows and then use different kind of misfit measurements for different windows, right? So for example, if on a Z component you may have the surface waves, right, the Rayleigh waves, which you might want to do frequency dependent group delay or phase delay, that kind of thing, right? And then you also have body waves, for example, direct arriving P or some kind of converted reflected phases, that kind of thing. Those body wave phases don't really have much of a dispersion, so you don't want to. You may just want to do a broadband cross correlation travel time measurements. So this kind of window file allows you to incorporate those kind of information into like a one file, and then the WPK is gonna just read through it, and then create the WPK for each of the component accordingly, according to the type of the WPK, the type of the misfit measurement, right? Um, and then I can just run it, right? If I just run it, it's going to create the WPK files. If I still go back to the, so that's the WPK. That's the WPK that's generated last time in the last video. So there are not supposed to be any differences. So if I kind of compare them, they should be identical, right? Oh, why am I seeing so much difference? Hmm. But anyway, I'll try to sort of look at that later on. But for now, let's just um, oh, I see. Because I changed The reason I'm seeing the difference is because this BAK file was created for a different starting value number. The beginning. So anyway, that's um, that doesn't really matter actually. So okay, so that's the second thing I want to talk about, right? And then um, the third thing is about the surface wave kernels. So let's look at the uh, two new two new directories in the in the in the FWF forward wave field directory. These two directories, right? sfrc02.z and sfrc03.z. These are the two stations. One, this is SF. So sfrc02.z is located here, and then RC03 is located here, right? So if you think about it, RC02 is acting as a virtual source, and then RC03 is kind of acting as a receiver, right? And then we're applying a vertical force downward in the positive z direction, that's downward, at RC02. And then RC03 is acting as a receiver to record the Rayleigh wave. So, so, so if we sort of look at the input files for the SW4, and that's the input files. So you still got the refinement keyword here, and then everything else is like similar, except that the source here is has a source time function that's given by this STF file, and then Fz equals it's a body force, right? So Fz equals to 1. That's body force in the z direction, and then the the scalar moment, the scalar number is 1, right? Um, I'll come back to this problem later on, right? So if you specify this scalar as a 1.0, then you're not doing any scaling to the wave field. So the wave field could be quite small. The strand fields, the displacements are going to be really small, right? 10 to the minus 17, 18th power, that kind of thing, right? So very small number. And then the variable is not velocity anymore. It's displacement, right? In the last video for the source 100001, it was a velocity, right? The variable was I'm recording at the receiver is velocity, but here it's a displacement, right? The reason is because the source time function. The source time function is actually low pass filtered direct delta force, a delta function, right? So usually for a natural earthquake, you're not supposed to have this kind of a but for that 10001 source, it's the source time function is the integrated Gaussian, right? It has a ramp, right? But this one is not a ramp. This one is a direct delta, so it comes up and then comes down, right? So here you have to use the displacement. So the frequency dependent group delay measurements are measured on the displacement. Group delay measurements are made on the displacements. So and then if we look at the input file for RC03, that's sort of the green tensor, right? The strand green tensor. Then it's pretty much identical, except that the source location is kind of changed. The source and receiver location are kind of switched, and then everything else is like identical, right? And then we can just run this code, and then we can get the strand fields, right? Once we get the strand fields, we can run our WPK code, and then let me just make sure. Let me just see if I got the WPK right. Still different, right? I have no idea, but I think it's not gonna matter. Um, once we have finished running the WPK code, once the WPKs are generated, we can just uh, run the data sensitivity kernel code DSK without any kind of a change. Everything else is like identical to before, right? So this data sensitivity kernel code is unchanged. It's there's nothing different from last time. And then the last thing that has to be modified is the call to the input file to. If we want to plot out the kernel, now there's more complexity that's kind of involved because it's not a uniform grid anymore. You have two composite grids. Suppose we want to take a cross section. That cross section, if we take a vertical cross section, that vertical cross section is going to cut through multiple grids, right? And then each grid is going to have a different grid spacing, that kind of thing. So, so this AVK code can handle that. But when we generate the output files, but when we actually specify the inputs and then specify the when we actually try to plot the outputs in the MATLAB, we have to sort of write some slightly more complicated scripts. So 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 the avk.csh script is not really different. We are still just using the inputs are kind of the same, but the only thing that's kind of different is this thing, this input file that specifies the cross section, right? So if I want to look at the this file, um, for this particular file, it's still the same as last time, right? It's still the same as last time because this is for the body wave example. So we are looking at the cross sections at constant x or constant y, right? But don't forget that these numbers are for the grid number after decimation, right? So it's not before decimation, it's after decimation, right? So for the body wave, it's not really, it didn't change actually. But for the surface wave, especially if you want to take a map view plot, uh, that's the input value for the map view, for the cross sections, for horizontal cross sections or map view plots. So these are, so the first column is specifying the kernel type, right? So for body waves, we are looking at the P kernel, P sensitivity for most of the arrivals, and then S sensitivity for the converted wave, right? That's for the last converted wave, for the last WPK. And then, but for S wave, for the surface waves, for the radial wave, we are looking at the S sensitivity. So now the first column becomes a 1 now, and then we have just a 1 window, and so. Yes, we have just one window, but we have two different frequencies, right? 0.5 hertz and 2 hertz. And each frequency is going to correspond to 1 WPK. So for the second number, if it's 0, then it's corresponding to the WPK of the 0.5 hertz. And then if it's 1, then it's the WPK for the 2 hertz, right? And then that's the Y at this particular cross section. And then when we specify the Z or constant Z slices, the Matthew plots, we have to give it two numbers. It's not just one number anymore. It's first we have to give it the grid number, right? Is the Z slice inside of the bottom grid, which has a grid number of a grid ID of 0, or in the top grid, the refined grid? If it's in the refined grid, then the grid number is going to be 1. So what we are looking at is actually a grid number at 1. It's the inside of the refined grid, and then we are looking at the Z equals to 3, 4, 5, right? This is for the low frequency one. That's the 0.5 hertz kernel, right? And then don't forget that after decimation, the grid spacing is like 400 meters. What I was saying is that 0.5 hertz, the kernel is supposed to have the largest sensitivity at about 1.6 kilometer depth, right? So 4 grid points, 4 decimated grid points is exactly at about 1.6 kilometer depth, right? And then for the 2 hertz the kernel, the largest sensitivity is supposed to be at 400 meter depth. So when z equals to 1 inside of grid 1, then that's exactly 400 meter depth, right? So that's why this this input file underscore xsc has to be, this is how this file is supposed to be written. So to make sure that the AVK actually works. And then after that is done, we can just run the AVK code, and then it's gonna create all those um, so depending upon the last command line input to the AVK code, the output files are going to be named as with this particular prefix kv underscore all. Right, it's these files, and then we can just sort of try to plot them in MATLAB. Right. So what I've done is that I've written some scripts to reconstruct the kernels, right? To reconstruct the kernel cross sections. So what we have to do is to actually, so once we have loaded the output is actually text file in just one column. So small k is going to be a one column file, right? And then we have to sort of reshape that one column file into like two-dimensional matrix, that kind of thing. But this time we have to sort of split this one-dimensional column into like multiple parts, because it has like two different grids, right? So k1, which has a range that goes from 1 to this times nz1, this is for the bottom grid, right? And then this is for the top grid, right? So what AVK is writing out is just the cross section one grid at a time. The cross section inside of each grid from the zeroth grid, right? So if the cross section is gonna cut through the zeroth grid, and also the first grid, right? So AVK is just gonna write out the cross section inside of the zeroth grid first, and then it's gonna write out the cross section inside of the first grid, right? The top grid, and then we have to sort of split them into like two parts, and then reshape them according to the grids, the number of grid points in each of the directions for the two component grids. So ny is supposed to be the same, but nz is going to be different, right? For bottom grid, nz is going to be 113, and then for top grid, it's going to be 13, right? So these numbers are actually printed out as screen output when we call the AVK code, when we run the AVK code. So all we have to do is to actually sort of modify these numbers according to the screen output of the AVK, and then this code is going to plot out the body wave kernels like that, right? So the scaling is like all wrong. This four has the same scaling, but this cross section is supposed to be right in the middle here, but MATLAB has a sort of weird way of scaling all the plots. And then for the surface wave kernel, it's looking like that. It's looking like that. So this is actually a cross-section view perpendicular to the source receiver plane, and then this is a map view plot at the depth of the largest sensitivity for these two different kernels. Right. Yeah, I think that's pretty much everything I want to cover in this particular video. All right.